get recorded. So if you're out there and didn't come to class, too bad for you. Whoops. Whoops. All right. Okay, we are going. All right, so there are these various classes, right? You know about polynomial time. If you don't know polynomial time, there exists an algorithm. There exists the constant c, such that your algorithm for every input, your algorithm gives you the right answer in time the size of the input raised to the c. And that's polynomial time. And exponential time is the same idea, except it's 2 to the raise to some constant times c, some constant times the size of the input. And now we're talking about this class in here called non-deterministic polynomial time. All right? And you might ask, this sounds so stupid. Why are we doing this? But really, I would almost say of all the things we've done so far, this is likely to be the one that comes up in your life the most. If what you're doing is if you're working at the bank and they tell you to translate this data file to this data file, maybe it'll never come up. But if you're actually trying to solve new computational problems, there are books and books on problems that fall in this class. All right, it's just if you ask for think of a random computational problem, that you really want to solve in the world, it's likely in this class. And the thing is, when it's in this class, now there's a nuance to it, and it's useful to know this nuance. And the nuance is sometimes it falls down into polynomial, in which case you have a nice algorithm for it. And sometimes it goes up to be what we call NP-complete, which means, as far as we know, there's no polynomial time algorithm for it. And it's good to appreciate these things. All right? So first off, here, suppose you're working for the man. Hopefully in the future you're working for the woman, but and she gives you this new computational problem, right? And you want to understand, where does it lie in this hierarchy? Why? Because, as my father pointed out, if you can do it in poly time, it's probably practical. And if not, then it's not practical, right? So now, what does it mean to be in NP time? And you should know this. This is not saying it's hard. This is saying it's easy. It's giving you an algorithm for it, or at least, right? So what it's saying, right? So that's why this, if it's saying it's NP, means it's below the blue line, right? And what does that mean? That means if your boss gives you an instance to the problem, and your fairy godmother gives you a solution to the problem, then you can go to your boss, and your boss doesn't believe in fairy godmothers, and you know better not to mention her, right? But you can go to your boss and say, here's the solution to your problem. Your boss quickly in poly time can check, yes, I don't know where you got this solution from, but well done. Yes, it is a solution to our problem, and we're done. That's when the instance is a yes instance. It has a solution, right? Now you might say, why is it not symmetric? It's because when the instance is a no instance, it doesn't have a solution. So no matter how good or evil your fairy godmother is, she can never give you something that will convince your boss, one way or the other, right? There's no proof. There's no proof that it's a no instance. And there's no way to prove it's a yes instance when it's not. All right? And I told you that one of the things my father has curled on his rock, carved on his rock, is that if it's in the intersection here, if there's a proof of yeses and a witness, a solution of yeses, and a proof, a witness of no's, then likely it falls in, there actually is an algorithm. Of course, that would break all our banking systems if that were true, but let's not get into that. All right, so now we're going to talk about some way of saying that it's hard, right? There are any problem that's in poly time is an NP. Why? Because if you can solve it on your own, you don't even need a fairy godmother, right? Oh, and by the way, also, if it's an NP, it's an exponential time. Why? Because the solutions that these things have, their size is about the same size as the input, and so there can't be more than an exponential number of solutions, and you can just check each of them in exponential time, and that's called brute force. Right? Everybody with me so far? Yeah, but you're never with me. What? I feel you. What aren't you getting? It means non-deterministic polynomial time. And the non-deterministic part means that it's not determined what you do. You get to guess, or you get to have help from your fairy godmother. Right? And in this case, the help is she's going to give you proof. You have an instance. She is going to give you proof that it's a yes instance. She'll give you a witness. She'll give you a solution. Something that you can take to your boss to prove that it's a yes instance. Now the problem if you don't have a fairy godmother is that there are an exponential number of these solutions. Right? So each of these solutions you can check in poly time. You can check it, but there's an exponential number of them. That's all I got to say about it. So you kind of get that?
You said before about how you can't prove yes or you can't prove no.
Uh-huh.
Can you explain that part actually?
Can't prove. Oh, you mean you mean the intersection thing?
You're talking about yeah, I think so. Or if you're talking about it before.
Well, problems that are over here are, if they're yes instances, there's a proof that it's a yes. There exists a proof that it's a yes instance. And if it's over here, there exists the proof that there's a no instance. I think I skipped these slides, but guys up here, like the halting problem, the recognizable guys, if it's a yes, there's a proof that it's a yes. There's a proof that M halts an I. What's the proof? It's a halting computation, right? But the problem with that proof is it's a finite length, but it's arbitrarily large, right? So you can't brute force look for them all, right? Over the proof that the halting problem, that a proof that a Turing machine halts is a halting computation, right? You run it, that's a proof, right? But that proof could be really, really long. And it's so long, it could be as long as the integers, so you can't look at them all. Right? Each proof, like the integers, each proof is finite, but there are an infinite number of proofs. So you can't look at them all. That's what's happening up here. Right? Down here, the only thing that's changed is we require proofs to be of about the same size as the input. And since their proofs are smaller, if you don't have a fairy godmother, you can brute force look for them all. Yeah?
Is NP complete the same thing as co-NP?
No, not at all. Co-NP is the circle over here where there's a proof of the no instances.
And NP complete, is that outside of
NP complete we're going to cover right now. It's the guys who live in here. What's what? The question that was on test 3, will this program halt in 2 to the 2 to the 2 to the n time, can be solved in 2 to the 2 to the 2 to the n time. You just simply run it for that length of time, right? And that is bigger than exponential. Because it takes 2 to the 2 to the 2 to the n time to solve. And that's bigger than exponential. Yes?
Are you trying to say that this NP problem can be also done in exponential or computable?
Yes. Yes. Why can it be done in exponential time? My boss gives me an instance. I know that if it's a yes instance, they're out there somewhere. What's the definition of it being a yes instance? The definition is that it has a solution. It has a proof that it's a yes instance. So all I have to do is find it, right? And for each possible solution, I have a polytime algorithm to test that whether it's a valid solution or not. And so I just have to try them all. That's exponential time.
How can it be an NP problem if it's being done exponentially?
These are subsets. Things that can be done in polytime can be done in exponential time. Right? Things that can be done in exponential time are computable. But there are things that are computable that can't be done in exponential time. Question on test 3. There are things that can be done in exponential time that can't be done in polynomial time. Does that answer your question? Right? So what's this class? These are the class where you can do them in exponential time because you just try all possible solutions. Right? It's possible that you can do all of these things in polytime. You might have heard one of the big open questions in computer science is, does P equal NP? And that is, does this class equal that class? Or are there problems in here that take exponential time? And people believe that they're different. Right? Because it's non-deterministic polynomial time. You non-deterministically guess the solution, and then in polynomial time, you check that it's true. All right, so what does complete mean? Complete means if it's back to reductions. If I can, it's NP hard. NP hard means it's above this. And what does being above this mean? That means that if I had an algorithm for this new problem, then that would give me an algorithm for every problem that's an NP. Right? And you would be rich. Right? If you had an algorithm that could solve every problem in NP, it would, in some ways, it would really be bad. Right? We would no longer have privacy. There would be no longer a way for you to hide anything because people could just break open every door that every electronic door that you ever could form. All right? So it would be bad if these classes were equal. Because, all right, so here, everybody get that? These are the problems. They're at least as hard as everybody down here. If you could solve one of these, you could solve everybody down here. And then what's this set right here? Or here's just the saying. Every problem in P, the new problem is at least as hard as it. That's the definition of NP hard. Right? And Cook, what did Cook do? Why he's famous for this stuff is he proved that satisfiability was NP hard. All right? And the advantage of the fact that Cook did that for you is now if you want to prove something's NP hard, you just have to prove it's harder than SAT because Cook already proved that SAT was harder than everything else. All right? So we'll be doing reductions that say, if I had an algorithm for this new problem, then I would have an algorithm for SAT. And remember what SAT is? It's I give you a circuit and you want to know, does it have a satisfying assignment? All right, so NP complete, it's in NP, and it's NP hard, makes it NP complete. All right? And, of course, SAT's in there. All right, so what's the big picture here? The big picture is that industry has all these problems that it would love to solve. Right? One of the problems, I just made this up, this airplane problem. It's not well defined. It's just sort of a, hey, yes, industry wants to solve this problem. What's the problem? You tell me what requirements you want of your airplane. You tell me what you want it to cost to build, how much lift you want to do, all these various things. And then the solution tells you how to build it. Right? And the reason I say this is an NP is because given the requirements of the airplane, if you were to tell me how to build it, I could then build it and see if it fit the requirements, right? But there's so many ways to build an airplane. There's an exponential number of ways to build an airplane that unless the fairy godmother tells me how to build it, I might not be able to find how to build it, right? So that makes it a problem that's an NP, right? Does that make sense? And it's generic enough that you can imagine that this comes up all the time. Industry is looking for a solution to one of its problems. And if you were to hand it the solution on a silver platter, it would be thrilled and it would know that it had it. But there's just too many solutions and it doesn't know which one to try. Right? So you can see that this is something that comes up in industry. Right? So here's some other examples. Circuit SAT, I give you a circuit. A solution is a setting of the input such the output is true. Right? It satisfies the circuit. This one we told, I gave you a graph. You want to color it with, say, 3 colors so that every edge is bichromatic. Every edge has 2 different colors. Right? So the instance is the graph. The solution, the question is it 3-colorable or not? Can you color it with 3 colors? Yes, a graph is a yes instance if you can color it with 3 colors, and it's a no instance if you can't. So what's the solution? Right, here's a question that I've asked on a number of exams. All right, here's the question. Why is 3 coloring in NP? Right, and what you're supposed to say, well, given an instance, which is a graph, I know the instance is a yes instance, if and only if it has a 3 coloring. And if the fairy godmother were to give me a 3 coloring, I could easily check that it was a valid solution, so I would know that it was a yes instance. Hence, 3 coloring is an NP. Everybody got that answer? 3 coloring. Why is it an NP? Well, what's the problem? What's the 3 coloring problem? The instance is a graph. When is in each graph, every graph is either a yes instance or a no instance. When is it a yes instance? It's a yes instance when there exists a solution to it. In this case, a solution is a 3 coloring. Right? And how big are solutions? Well, they're about the same size as the input. Right? And if the fairy godmother were to give you a solution, in polytime you could check it. Right? Everybody get that?
So given a solution in what time would you not be able to check it? At what point does it go exponential?
Well, you could. The go-to exponential, I think, is a red herring. It's a misunderstanding because the exponential bit is where you have to check all the exponential number of solutions. But I'm not sure what it would mean to say that something was a solution if I couldn't check that it was a solution. Or no, maybe a solution, but it wouldn't be a proof, right? I guess I can imagine some situations. In fact, I can imagine graph theory questions where okay, this is a solution, but there's no way to verify that it's a solution. And I don't think we have enough time to go into the examples, but where it takes you exponential time to check that it does happen to be a solution, but it would take you exponential time to check it, right? So, for example, here's a problem. Suppose I have some other problem, and in order to solve this problem, I need to know a graph that is three-colorable. And the fairy godmother gives me a graph that's three-colorable. Well, she's given me a three-colorable graph, but it takes me exponential time to check to see if it's actually a three-colorable graph, right? And certainly, the halting, what happens more frequently is that, like the halting problem, the solution is too big, right? The reason you can't check it in polytime is because you can't even look at it in polytime, right? If I gave you a halting computation of M on I, it would be so big that you couldn't even look at it, right? Everybody good? Yeah. All right. So let's do another one. You might complain that York does a bad job scheduling your courses. Well, it turns out to be NP complete. So here's a problem. The input, why is this problem in NP? Well, what's the problem? The input says what courses do people want to take, what time slots there are, and what do you want to do? I mean, let's not even worry about all the other problems. And we also put in these two courses can't be scheduled at the same time because Jeff is teaching them both, right? And now what do you want to do? You want to schedule the courses in the time slots, right? So a solution is how to schedule them so that there's no conflicts, right? And if the fairy godmother would give you the schedule, you could say, oh, that's a really nice schedule, right? Just like you guys look at the schedule and you say, that schedule is really bad. You could also would look at it and say, that schedule is really good, right? But if you would have to come up with a better schedule, that could be hard, right? So here are a bunch of problems, right? And we could say they're all completely different problems, or we could link them together, right? The first thing we're going to do, it's going to take us a few seconds. First thing that we're going to do is not only can you reduce from one of these problems to the other, but really they're the same problem. Yeah?
So for the schedule problem, check yes every other schedule.
Good question. So if I were to ask, give me the schedule with the minimum number of conflicts, then that's a harder problem, right? It's not a yes-no problem. That's a how do I minimize problem, right? So if I were to ask, is there a schedule that has fewer than 7 conflicts, then that's a yes-no question. Either there is a schedule or there's not a schedule. And if I gave you a schedule, you could check, yes, it only has 7 conflicts or fewer, right? Now what you're leading to is the minimization problem, and it has an NP and a co-NP feel to it, right? I can give you a witness to prove that you can achieve 7 or fewer conflicts. But how do I prove that you can't have fewer conflicts, right? That's a co-NP question. You want to say, you want to prove to me that there's not a schedule that's better, right? And in co-NP, there's a witness of the no, but not a witness of the yes, right? I can prove to you that your thing isn't the best schedule by giving you a better schedule, right? But I can't prove to you that yours is the best. Did you follow that? That's the whole NP, co-NP sort of thing. How do you prove that I can, in NP, I can prove that I can achieve this, but I can't prove that I can't get better without checking them all.
So all of these examples, you said when the fairy godmother gives you a solution, it takes you exponential time to check that solution.
No.
Just polynomial.
Non-deterministic polynomial time. Once you guess it, you can check in poly time.
Was there, I kept hearing exponential.
Yes, there are an exponential number of solutions. So to check them all takes exponential time. Right? Here's my instance. Here's my instance. Here is an exponential set of solutions. So I can say, is this a valid solution? Yes, no. I can do that quickly. Is this a valid solution? Yes, no. I can do that quickly. But there are a lot of them. So doing them all takes exponential time. You want to talk to me.
So essentially, if we have a problem that can't be run in like a really easy algorithm, but we can get a solution that can be run in non-deterministic polynomial time, then we say it's NP.
No, you didn't say it's an NP.
It's an NP.
To prove that it's NP complete, you have to be able to do a reduction.
Okay.
All right, so here we're doing reductions to prove that these problems really are just the change of names, and they're the same. And then we can prove Cook's theorem, which says, what is the airplane problem? It's a generic NP problem. And if you can solve this generic, or this is just the definition. If you can solve the generic NP problem, then you get a free lunch. What's this? This is Cook that says if you can solve SAT, you can solve the generic problem. And then we're going to do what I think is tremendously fun, and I'm sure you all will go home and tell your mothers about it, is that if you can solve 3 SAT, you can solve circuit Salif solubility. All right? And so that's what we're going to prove. And then what's the truth? The truth is people believe that there's no free lunch, and hence there's no fast algorithm for the airplane problem, and hence there's no fast algorithm for SAT, and hence there's no fast algorithm for 3 coloring or scheduling. Right? That's the belief. All right? All right, what is an optimization problem? It's you're given an instance, maybe a desired cost. What's the desired cost is, which is how few conflicts are you willing to tolerate in your schedule, right? This is addressing what he was talking about, right? And then for the instance, there's an exponentially large set of possible solutions, right? And there's a definition. A solution is either valid or not valid. Valid solution to this instance or not. And it may have a cost associated with it. How many conflicts are there? Right? We could add good schedules that have lots of conflicts, good schedules that have a few conflicts. So there's a cost associated with it. Right? And the goal is, given an instance, to find a valid solution that optimizes the cost, right? Either minimizes or maximizes the cost, depending on whether it's a minimization or maximization problem, right? So that's an optimization problem. And what are we doing? We'll be doing this in 3101, right? In fact, 2/3 of 3101 is solving these problems, all right? So, but what are we doing now? We're getting rid of the cost, and or we're making costs. We're saying, is there a solution that meets some threshold of cost, right? We're trying to make it into a yes/no question. How do we make it into a yes/no question? Is we either has no cost and we say, is there a valid solution? We don't care about its cost, or we include a minimum cost and we say, is there a valid solution with this minimum cost? That's a yes/no question, right? All right, all these problems have a common story. Large space of possibilities, tiny fraction of these possibilities satisfy the constraints, brute force takes too long, no feasible algorithm is known. If one had a fast algorithm for one, then they have a fast algorithm for all of them. If one doesn't have a fast algorithm, then none of them do. right? Does that make sense? Course scheduling, all right? So what's the problem? You have a bunch of time slots, you have a bunch of courses, you want to schedule the courses so everybody's happy, as we talked about. One thing you could do is you could try all schedules, but there are too many. As soon as you have 50 courses, there's more schedules than atoms in the universe, so that's hard. Is there a fast algorithm? People think not. We've been trying to prove that, we can't prove that there is, we can't prove there's not. Right? It's one of the big open questions in the field. Graph problems. I told you have a bunch of nodes and edges. Can I color it with 3 colors so that every edge is bichromatic? Right? Is one algorithm is you try all colorings, but there are too many colorings. Right? Is there a fast algorithm? We don't think so.